Welcome everyone. My name is Saqib Shahzad and I will have the privilege of presenting my analysis of the COVID-19 dataset. I have used data from the COVID Tracking Project, which is one of the leading reliable sources for data on this topic and is also used by the Johns Hopkins University. This presentation is an effort to analyze and forecast the number of daily new cases using the time series forecasting models like ARIMA, VAR, and deep learning models like RNN, MLP, and ensemble models. This graph shows the daily count of confirmed cases and deaths over time starting from March. We can see that the exponential growth of the pandemic is still in its peak. The sudden spike we see in June and July might be due to more people getting tested. Correlation of positive cases to death in US is 0.54, which shows a positive correlation between the confirmed cases and deaths. Here we can see the daily count of positive cases as well as deaths in the state of Maryland. We can see a peak in the daily cases in April and May, but the state has been slowly flattening the curve. Correlation between daily cases and deaths in Maryland is 0.74, which shows a very strong correlation between positive cases and death rates. Positive percentage is measured by daily confirmed positive cases divided by total testing done multiplied by 100. We can see from the graph that US has dipped below 5% after hovering at around 20% for much of March and April, and Maryland positivity rate is below 5%. Here we are checking if the time series data is stationary or non-stationary. The mean at two different time points are very far apart, which is evidence toward non-stationary. Using the ADF test, we can see that the p-value is 0.09, so we fail to reject non-stationarity at 95% confidence and conclude that the time series data is non-stationary. I also plotted the ACF between observations at the current point in time and the observations at all previous points in time, as well as the PACF for observations made at 2 points in time. We can see that the ACF decays geometrically, whereas the PACF has only one significant lag, suggesting AR1. The spectral density has a peak at 0 and a small wave, which could mean seasonality in data could be non-stationary. We used differencing to remove the series dependence on time, and after applying first order differencing, we did the ADF test again to check for stationarity. Here you see both the original and difference series plotted. We can see the correlation of the time series with its past values. The p-value is 0.0, which means the data is now stationary post differencing. Here we use the ARIMA model to forecast the COVID values of US for 10 and 60 days. Based on the AIC and BIC values, we concluded that the favored values for ARIMA is when autoregressive term is 1 and the differencing term and the moving average term is 0. This is the best model that has the least AIC value. Here are the short-term forecasts and the long-term forecasts from the ARIMA model for MD and US. The forecasted values obtained from ARIMA model are very close to the actual test data. Looking at the forecast for Maryland and US, we can say the trend is continuing to steadily increase, but in smaller intervals. Here on the top left, residual errors seem to fluctuate around a mean of 0 and have a uniform variance. On the top right, the density plot suggests normal distribution with mean 0. On the bottom left, all the dots should fall perfectly in line with the red line. We can see there are no significant deviations, which would have implied the distribution is skewed. Bottom right, finally, the corollagram shows the residual errors are not autocorrelated. I have used RNN with Keras framework using 4LSTM layers here to model univariate time forecast, time series forecasting. I have used MSC as loss function with a batch size of 32 and 100 epochs. Using this model, I have plotted the real versus predicted values. We can clearly see the actual values follow the predicted trend. We can see the model's RMSE and ASC values here as well. Accuracy for RNN forecasting for MD is 78%. The graphs show the forecasting for 10 days and 60 days ahead in Maryland. The short-term forecast shows continuation of the current upward trend. Long-term prediction of the RNN model turns downward to negative number of cases, which is not realistic. So we should not use this model for long-term forecasting, and the trend seems to continue. For ensemble model, we combine the best predictions from ARIMA and RNN. We can see that the ensemble model performed better compared to all the individual models because this model gave more weight to the accurate model predictions than the less accurate ones, as well as dynamically adjusted its weights. Moving on to multivariate analysis, we include the data for confirmed positive cases, deaths, hospitalizations, and on ventilator counts. We again analyze the data for stationarity, and using the ADF test, we can conclude the data is non-stationary because the p-value is greater than or equal to 0.05, and ADF statistic value does not reach the critical value. After applying first order differencing, data was still stationary. So we applied second order differencing to make the data stationary, and doing the ADF test to check for stationarity, we can confirm the data is now stationary. We proceed with vector autoregression model. We iteratively fit increasing orders of our model up to 9 and pick the order with least AIC, which is 3 in this case, checking the serial correlation of residual using Durbin-Watson statistic. The serial correlation seems to be good here, so we are proceeding with the forecast. We can see the RMSE and ASC values for VAR models here. The accuracy stands at 89%. The forecasted value is plotted in blue compared to the actual values in orange. We see a steady climb for US short-term forecasting for hospitalizations and positive cases. Whereas for Maryland, short-term forecasting for hospitalization, positive cases, and deaths seems to be steady. This is the long-term forecasting for US and Maryland. The forecast for Maryland shows a significant climb in hospitalizations, confirmed cases, and deaths over the days, whereas the forecast for the positive cases for US seems to be dampening. Whereas the RNN model for multivariate analysis gives an accuracy of 78%, the plot shows the forecast for the positive cases in red and the actual number of cases in blue. The short-term forecast has a significant peak for both Maryland and US. The long-term forecast for US is dampening, whereas Maryland is following the trend of the actual cases. For ensemble model, I have combined the best predictions from VAR and RNN models. We can see the ensemble predictions in purple, whereas the actual values are in blue. The RNN forecast is in red and the VAR forecast is in green. We can confidently say that the ensemble model is performing better than the other models. In conclusion, the RNN was our best univariate model and the VAR was our best multivariate model. Thank you for giving me the opportunity to present my analysis for COVID.